number 4, Origin of Life Theories and Cultural Implications, MCPB 36-4.
Hello. Today I'd like to begin to explore the question that's being bandied about quite a bit these days. Is the Earth the only planet with life forms? Since all we know about life is life on the Earth and from the Earth, we might explore the condition living as we know it and the possibility of its origination anywhere else in the cosmos. Before we delve into this question, though, I think we need to consider exactly how science works. How does science get its answers? I hesitate to say we're going to learn the scientific method because you might get the idea that there's only one scientific method and nothing could be further from the truth. I prefer to call it model building. We've all had some experience with models. As a child, we played with models of one kind and another. Here we have some dolls. These are made of acorns and peanuts. Most girls play with dolls of one kind and another. If they play with baby dolls, they learn to change its diaper, feed it, dress it. These little figures here might be used to play games with, to walk around a dollhouse or something like that. Model airplanes, most boys play with model airplanes or model cars. And a model airplane must take in some of the principles of aerodynamics or they won't fly, even if it's simply a paper airplane that you fly at the teacher in the front of the room. Dolls' houses, if we were going to walk these little models around in a doll house, must be made to a certain scale. They're made to a certain scale of figure, a certain scale of furniture. If the scale's off, they don't look right, and you can't arrange the rooms properly, and you can't walk the little figures through. Architects build scale model houses too, and draftsmen. Here we have a model house that was built by some of our AID students at Catonsville. This particular model originated, I'm sure, in someone's imagination. But in order to see exactly how it looks and how it fits on the lot and how the rooms go together, it had to be built into a model. Things had to fit. It's possible also to decide how the furniture can be arranged in these rooms. Or traffic patterns, how will they work? The builder, the contractor, can probably decide by looking at this model just where he should place electrical outlets, and the plumber can decide where he'll put in the plumbing fixtures. The landscaper can decide where he's going to put the trees and shrubs and so on. Here we have another model. This is a little koala bear. Now, this looks very much like the real thing, but I think I'd much rather stroke this one or go to bed with this one than the real thing. And our final model here is a model of an amoeba, a plastic model, much enlarged. The koala bear was very close to the same size. Here we have a model that's much enlarged. The scale is much greater. Now, no matter what kind of model we use, if we're talking about planes or cars or houses or whatever, I don't think any of these ever go into production without first being tested for feasibility of design. How do you build a model of anything? All of the models that we've been talking about are concrete models, but a model can be an abstraction or an analogy. We mentioned in our discussion of the electron, Schrödinger's mathematical model of the electron. Now, this model was based solely on mathematical calculations. We did see that a concrete model could be based on his calculations, and it would look something like this. You'll remember when we talked about the electron. Now, no matter what form a model takes, it stands as a representative of the real thing. Therefore, some knowledge about the real thing is necessary before a model can be built. Observations have to be made, measurements have to be taken, and relationships have to be noted. Obviously, some question directs these activities. The scientist calls his question a problem. Sometimes the most difficult part of his job is the statement of the problem, asking the right question. What and how questions are usually more fruitful and give us more answers that are more easily tested. A scientist almost never asks a why question. Unless a why question converts to how or what, then it's probably not testable, and it's probably better explored by the philosopher or the theologian. Now, all observations are dependent on our five senses. We use them either directly or indirectly. At first, that's all we had to use, but then technology extended our senses, and we're able to ask questions today that were unthinkable a short time ago. With microscopes, we can see things that are much too small for the naked eye. We're almost down to the molecular with microscopes now. We can convert radio waves to audible range so that our ears can sense them. We can take photographs with light waves that are out of our visual range. Why, we can take a photograph of an area and show that someone's been there and gone. The heat left behind is recorded on infrared sensitive film. All of this information is recorded for others to check and verify. These clues about the unknown are our data. Now you'll notice I said our data, so we know that data is a plural word. Data don't advance our understanding very much unless we assemble the bits and pieces of information into some kind of a framework. A detective gathering clues at the scene of a crime usually has a question in mind. Who's responsible for the crime? Unless he establishes relationships between different clues, he can't begin to make a guess as to the culprit's identity. Once he does establish this relationship, he makes an educated guess as to the probable solution to the mystery, and he sets about the business of proving it. In science, we call our educated guess an hypothesis. Just as the detective would reenact the crime, we reenact the experience to see if our pieces fit in our framework. The detective makes a model of the scene based on his observations. So you see, in a way, we could say that a model is really an hypothesis that can be tested. Once the scientist sets up his hypothesis, sets about the business of testing it, he reenacts the experience, and he calls this his experiment. If our findings are consistent with our hypothesis, then we can make predictions. That means we can answer some questions that arise from similar situations. If the hypothesis holds up through many tests, and if the predictions made with it hold up in all cases, then the hypothesis may be called a theory. Even then, it's subject to constant scrutiny and modification as new information is added. Please understand, a theory never becomes a fact. Once we've answered questions and made predictions, we usually open the door to many more new questions. There's always this possibility that one question will open the door to many more. This is what keeps scientists searching. Let's go back and recapitulate. Basically, the steps in scientific methodology are: 1, the statement of the problem. The problem is in question form. Then there's a formulation of hypothesis, and the hypothesis is the answer, the probable answer to the question in the problem. Then an experiment is designed to test the hypothesis. Once the experiment's set up, then 4, we collect data. These are our clues about the possible answer. Once all the data is in, then we begin to put it in a framework. We draw conclusions. And as we draw conclusions, we always make a statement about whether or not the hypothesis is valid or invalid. Now, negative results do not mean that it was a bad experiment. They may be just as valid as positive results. We need to know what we know as well as what we don't know. The elimination of one question gets us closer to the answer. Once the conclusions have been drawn, then we can begin to make predictions about what might happen in a similar situation. Now, please remember, the order here is not sacrosanct. It's just a listing of the elements that are usually found in any scientific model building. As background, I'd like to explore man's concept of the universe and his role in the universe as he saw it through the ages. I think it helps us to keep our perspective if we realize how limited we are in our observations and how drastically our ideas can change as we open new doors of discovery. Also, cultural influences greatly affect the acceptance of new ideas. I think if we're really open-minded, we'll see that this is still happening today. We seem to poo-poo the ideas of the past and think that these people didn't have the same abilities that we have. But the culture still influences our thinking and the acceptance of new ideas. We look at primitive cultures. There are some still with us today. We noted one once before when we were looking at Bullchild and his paraphernalia. Remember the North American Plains Indians? These are primitive peoples, and all primitive people seem to endow the sun, moon, and stars with a kind of consciousness. The sun, moon, and stars were supernatural beings who spoke to men in visions. In all cases where we've seen examples of this from primitive peoples, we've found that the sun was the major god, and all other heavenly bodies were lesser gods. And these gods' attentions were always directed toward the earth, and man was the ultimate recipient, the center of the universe. This was man's model of the universe, with himself at the center. So we say man's universe was anthropocentric. The ancient Greeks' sun god, Helios was his name. He spent his whole day driving a chariot bearing the sun across the heavens. These were the days of Homer. Homer's universe extended to the top of Mount Olympus. Today, astrology still operates on the premise that heavenly events function mainly to control man's destiny. In the 6th century BC, there were some Greek philosophers who regarded heavenly bodies as physical objects, not gods. And these physical objects, they said, revolved around a spherical earth. Now, remember, it took a long time for us to accept the idea that the earth was a sphere, so these men were way ahead of their time. New observations and calculations were added to this theory, and it finally reached its definitive form with Ptolemy in about 150 AD. So this was an Earth-centered universe. There were a few dissenting voices, but the Ptolemaic theory held among learned men for many centuries. This Ptolemaic theory received its first serious threat from Copernicus in the 16th century. Copernicus proposed a heliocentric universe. Remember Helios, the Greek sun god? This shift in the center of the universe from the Earth to the sun effectively expanded the size of the universe. Now the stars and the planets had different relationships, and the sun must be pretty far away. Pretty soon methods were developed that made it possible to pin this down, and in those days they pinned the distance from the Earth to the sun down to 87 million miles. Today we have better instruments, and we gauge that distance to be 93 million miles. Now this idea caused quite a furor among philosophers and theologians. In the 17th century, Galileo pushed the edges of the universe back even farther when he discovered that there were other stars, and he found new ones with his telescope, ones that had never been seen before. Advanced technology. Now he reckoned then that the sun might be a star, and that all those other stars might be suns too, simply suns that were very far away. What a blow to man's ego. Not only was he not the center of the universe, his sun wasn't either. This was so hard to accept that the Inquisition forced Galileo to stop making observations, and he had to recant on those things that he had already said were so. He had to pretend he didn't see what he saw. Now, we've seen how ideas have grown as technology opens new avenues of exploration. We've also seen that the culture of the times affects the acceptance of new ideas. We mentioned once before that Democritus's idea of the atom was shot down by semantics. Man, so far as we know, is the only creature who's aware of himself and also aware of his knowledge. He's also the only creature aware of what he doesn't know. So he seeks ways of explaining the unknown. Contemplation on the question, is there life elsewhere in the universe, raises another question. How did life arise on Earth? This is a fascinating study of man's method of dealing with the unknown, the attempts to answer that question, how did life arise on the Earth? This is a study of men with controversial ideas that were at odds with the culture of their day. We've already discussed how man's concept of the universe has changed from the ancients to the 17th century. Again, first as a man-centered universe with heavenly bodies taking interest in man and his activities, then moving to an earth-centered universe with the earth at the center, and moving on from there then to a sun-centered universe. Our own Western tradition is interwoven with Judaic-Christian attitudes. As George Wald points out in his Scientific American article, men are used to making things. So the way to explain the presence of anything is to assume that it was made, that it was probably made by a special creation, and the creator was a maker of things with greater skills than man. An account of this creation is found in the first book of the Old Testament, Genesis. The illustrations you're seeing here are from a 16th century Bible. And this is the first day. On the first day, God created heaven and earth. Now, we don't really know exactly what segment of time a day meant here, because this is based on a translation, and the calendar using days was not invented until the time of Caesar, which was many centuries after the ancient Hebrew account was written. On the second day, God separated the firmament and the waters. And on the third day, he made the dry land and plants. On the fourth day, he made the sun, the moon, and the stars. Now, you can see in this account the earth came first before any other heavenly body. On the fifth day, he made the birds and the fishes. And on the sixth day, he made the land animals, and finally, man. Now, in this accounting, life appears on the third day, first as plants. Then it develops as fishes and birds, then as land animals, and finally as man. Now, the biblical account doesn't say that God created plants and animals directly, but that he bade the earth and the waters to bring them forth. This last statement made possible the development of one of the first theories of the origin of life by natural means, the theory of spontaneous generation. Actually, this theory had its beginning back with the Greek philosophers again. We seem to always get back to them. In the 6th century BC, the Greek philosopher Anaximander said that he thought the first animals arose from sea slime and that men arose from the bellies of fish. Aristotle, you'll remember, was living during the 4th century BC. He pondered this problem also. He pondered lots of problems, and he was really a great scientist. He made all of his hypotheses based on his observation, and he set forth a hypothesis of the spontaneous generation of life. What sorts of observations led him to this conclusion? Now remember, he didn't have available to him the tools and techniques that we have. If you leave the garbage out, after a while, you can see maggots crawling all over it. After a warm spring rain, you'll find an empty marshy area will be teeming with frogs where the day before there were none. An egg, which is seemingly inert, will in some cases bring forth a chicken. Now, if you don't know what we know today about reproduction and the life cycles of those organisms that don't bear their young alive, the obvious conclusion is that they sprang from non-living matter. The maggots from the garbage, the frogs from the mud, and the chicken from the egg. In those days, there was no problem about which came first, the chicken or the egg. It was obvious. Now, Aristotle explained this phenomenon by assuming that there existed an active principle that produced living things when the conditions were right. He didn't consider this principle a substance, only a capacity to do something. You know, I think it's kind of interesting for us to note right here today, our concept of energy has the same explanation. Energy is defined today not as a substance, not as a thing, but as a capacity to move substances. Aristotle felt that sunlight, decaying meat, and mud all contained active principles, all contained these capacities. The idea of spontaneous generation held sway for many years. As late as the 13th century, people really believed that geese originated from certain fir trees that had come in contact with ocean water. And there are pictures in the literature to show how this happened. By the 17th century, experimentation was beginning to be the way to support arguments for hypotheses. Von Helmont, a Belgian physician who later conducted some excellent experiments with plants, did a very poor one to test spontaneous generation. He wrote a recipe. His recipe was for the production of mice. You took one dirty shirt, one handful of wheat grains, you placed all of these ingredients in a dark place and you let them stand for 21 days, and voila, mice appeared. Now, the shirt had to be dirty because it was thought that human sweat was the active principle. Now, this seems pretty silly to us today. What was wrong with his experiment? A scientific experiment is one in which all the variables are accounted for. For von Helmont's experiment, at least two setups were required. One in which the shirts and the wheat kernels were sealed from outside influences that might affect the experiment, and another one where they were left open to any other influences. His was not a controlled experiment. A controlled experiment is one in which all variables are held steady and only one variable is tested at a time. Now, he could have sealed wheat kernels and a clean shirt in one box. In the other, he could have sealed a sweaty shirt and wheat kernels. We know he wouldn't have produced mice in either one of these, and then he would have had to ask a new question. He would have found that that was the wrong question to be asking, and he would never have published his recipe. By the mid-17th century, a more modern scientific approach is seen in some of the experiments of Francesco Redi, which you find in your textbook. I do hope you'll read those very carefully. Redi was a biologist and a physician in Florence, Italy. You can see this is a very international enterprise. Each time we mention a name, it seems to be from a different country. Redi was experimenting with spontaneous generation about the same time that Galileo was studying the motion of the stars and the planets with his telescope. Now, this was a dangerous time to advance ideas that seemed at odds with the church, so treatises were very carefully worded. Redi states in his experiments on the generation of insects, "Although content to be corrected by anyone wiser than myself, if I make erroneous statements, I shall express my belief that the earth, after having been brought forth the first plants and animals at the beginning by order of the supreme and omnipotent Creator, has never since produced any kinds of plants or animals, either perfect or imperfect." He knew that he must offer some evidence for this, so he set upon an experiment in which he put dead meat in some jars. Half of the jars he sealed and half he left open. Only the open jars contained maggots after several days. He concluded, "These worms are all generated by reproduction, and the putrefied matter in which they're found has no other function except as serving as a place where animals lay their eggs and in which they find nourishment. Now, what Reedy was saying here was that all life comes from pre-existing life. This statement is known as the theory of biogenesis. The controversy was not over, however. In the 18th century, lens makers began to magnify substances, and one lens maker from Holland, von Leeuwenhoek, described in great detail his little animalcules. He discovered these little animalcules in drops of water and in putrefying broth, and he concluded that they dropped in out of the air. An Italian abbe, Spallanzani, boiled some nutrient broth, sealed it from the air, and demonstrated that no putrefaction occurred. This controversy caused a rebuttal from Needham, an English Jesuit who also had done some experiments in which he heated some fluids. His fluids contained small food particles. He sealed these, and in a few days his test tubes were just swarming with microorganisms. So he concluded that spontaneous generation does take place, and he cited the biblical reference that God bade the earth and the waters to bring forth life. And he said this directive was never rescinded, so there's no reason to believe that this couldn't happen, and no heresy was involved in believing in spontaneous generation. He claimed that Spallanzani had heated his liquid to such a high temperature that he destroyed the active principle. Spallanzani countered with the suggestion that Needham hadn't heated his tubes at high enough temperature to kill the living things that were already there. This controversy raged until 1860, when Louis Pasteur did his very famous experiments. They're really a modification on Spallanzani's experiments. He did these experiments in front of a very august gathering of scientists in France, and this wrapped up any controversy, any further controversy. Now, exactly what sorts of variables are we seeing in this setup? If we take a look at the setup, you can see that the flasks have been treated in different ways. A close look will show that some are completely open to the air, others are sealed off, and others have a limited pathway for the air. So we have to account for our variables if this is a good controlled experiment. So one of the variables is the path of air. You can't see it, but I can tell you that these flasks have all been treated in a different way as far as heat is concerned. So heat is another variable. Now, what sorts of observations can we make? What can we collect as our data? Well, we could open up each of the flasks and make a microscopic examination, but then we'd have to terminate the experiment. I think we can just make some observations of the differences in the flasks and base our conclusions on observable differences. What's different about these? Well, some seem to have a different color, and that color is really determined. Let's collect observations here. That difference in color is really determined by turbidity, which is just really another way of saying cloudiness. We can see that. Those that are open, we have another sense that becomes assaulted. You can tell putrefaction by its odor. So we can tell if putrefaction has occurred in those that are open by seeing if there's an odor. Let's take a look at each of these and see what questions may have been countered with this experiment. We have to account for every variable. So we have to have an overall control. In this overall control, I think you can probably see the turbidity a little bit better if I use this black pointer behind it. As you can see, you cannot see through the liquid. because of the cloudiness. This is our overall control, and in this we've done nothing to the broth at all. We have not heated it, and we have not obstructed the air to it in any way at all. In this flask, which is really a repeat of Spallanzani's experimental, or his control, we have a flask that was heated for 15 minutes, but no obstruction to the air. In the third one, we have what amounts to Spallanzani's experimental. Now you can see that this is less turbid. But Spallanzani's experiment was not as acceptable as it might have been because the vitalists said he had cut out the active principle by excluding the air, that the active principle must be in the air. A little bit later, when oxygen was discovered, and it was discovered that most living things need oxygen in order to survive, then even the mechanists said the problem with Spallanzani's experiment is that he has excluded oxygen, so nothing can live. Then a little bit later, when it was obvious that some things may live, and as you can see there is some little bit of turbidity in this particular flask, it was more difficult to explain, and maybe there was such a thing as spontaneous generation after all. How did Pasteur counter these arguments? He used a different method of heating, for one thing. We have modified his somewhat. We've used an autoclave, but it amounts to the same thing. We have pressure cooked our media in this case. Pressure cooking takes the media to a higher temperature by putting it under pressure so that boiling occurs at a much higher temperature. We know that there are some forms of microorganisms that are very difficult to kill. They can survive boiling temperature. And in order to get rid of them, to kill all of them, you have to take it to a higher temperature. This has been autoclaved. This is one of Pasteur's controls, autoclaved and left open to the air. Now, there isn't great turbidity in this, but if you look closely, you can see that mold is growing on the top. We're getting a different species of growth, but there is some growth. Here, we have an autoclaved sample that's been sealed, as Spallanzani's was, and there's no evidence of growth. If we compare this to Spallanzani's, you can see that there is just a little bit of difference in the turbidity. Do you see? Now, Pasteur had another control. He had this one, where he limited the passage of air. As you can see, he has a straight tube. It was his contention that living things dropped in out of the air. So some things dropped in here, but not as many as in the original control. You can still see the pointer through it because there was a limited path they could follow. Here we have a C-shaped tube. If these organisms fall down into the flask full of medium, then it would not be possible for them to fall in through this particular setup. And as you can see, it is clear and shows no evidence of turbidity. In this one, we have an S-shaped tube. This is a modification on Pasteur's tube, and we can find some of these in the Louvre at France right now. They have sealed the ends, however, because evaporation was beginning to eliminate some of the media. But his contention was that there was trapping of microorganisms right here in this bend of an S-shaped tube, that this acted as a trap, and therefore the media would stay uncontaminated. In order to prove this, he ran a little bit of the media up into the tube, as we've done here. We ran the media up into the bend of the tube to see if there really were things trapped there and let it sit for a day or two. And as you can see, we begin to see evidence of turbidity. Now, based on your observations, what are your conclusions about the origin and the source of microorganisms? His conclusions were that hands, glassware, air, all of these things contain microorganisms that contaminated foodstuffs. This idea had many far-reaching consequences. We've been able to make predictions with it. Out of these conclusions have grown the pasteurization of milk, the sterilization of foods to preserve foods. Acceptance of the theory of biogenesis opened the door for another theory. If all life came from pre-existing life, then living things must have had ancestors. Each individual wasn't an act of special creation. Where did it all begin? The time was ripe for a theory of evolution. Actually, as far as the question about how did life originate was concerned, the theory of biogenesis laid to rest any consideration about the origin of life for many, many years. If all life came from pre-existing life, then life had always been, and there was no question to ask. But then in 1924, a Russian biochemist named Oparin argued there's really no fundamental difference between a living organism and lifeless matter. We have up to this point been discussing the difference between living and non-living and a hierarchy of matter that rises with increasing organization of matter. Has this organization always existed? Has the hierarchy always been in existence? This is a question that piques the imagination. It's been said that the only constant in the universe is constant change. We live at a time in history in which change is so accelerated that there are few of us that don't accept this constant. We have a name for the process of change through time. I am talking, of course, about evolution. And today it's generally accepted that the hierarchy of matter is a continuum that traces evolution. So if we start with the evolution of the elements, we're talking about stellar evolution. Now we've traced man's concept of the universe up to the point where questioning had to stop due to cultural pressures. But as more evidence began to accumulate, the ideas began to pressure the culture, and these ideas would no longer be denied. Increased use of telescopes and new ways of interpreting the motions of heavenly bodies forced the acceptance of the Copernican solar system. By 1920, enough information about stars in the Milky Way made it quite apparent that our sun is about 35,000 light years away from the center of a galaxy which is shaped as you see. Aha, now we have a new center of the universe. The universe was galaxy-centered or galactocentric. This center of the universe didn't last very long. The tools and techniques that had been developed very quickly took us beyond our galaxy to other galaxies. And since 1950, with the use of radio astronomy, the universe has extended to galaxies 4 billion light years away. There seems to be no end to it, and there seems to be no center. So today, the universe is acentric, that is, without a center. Where did it all begin? How did it all begin? The ultimate beginning can only be explained by theologians, but the first stages lend themselves pretty well to hypotheses. It's possible to pass the light given off by an element through an instrument that will analyze its spectrum. Now, the pattern that's given off represents an atom's structure and is always the same for any specific element. Let's take a look at this chart. Here you can see a white light that acts as a source, and if we pass the light from that source through a slit, the beam of light then can be passed through a spectrum, and it breaks up into the spectrum as we know it. This is because different wavelengths of light travel at different speeds, and when they're bent, they travel through the prism at different rates. Therefore, we break it up into the spectrum. We've all seen the spectrum. This is what you're seeing when you see a rainbow. The water droplets in the air act as a prism. Now, suppose we have a hot gas here. This is at the light source. The light given off here passes through the slit, then through the prism, and we get a pattern much as you see here, which is a series of bright lines. Now this would be the same for this hot gas anytime the gas contains the same elements, so the pattern remains the same. Let's take a different, for instance. Here we have the light source with the gas superimposed between it and the slit. The implication here being that this is a cold gas or a cool one. Now what happens? The light passes through the prism, and here we have the full spectrum with a series of dark lines. If we take a look at the position of those dark lines on the spectrum, we see that they're the same as the bright line on the bright line spectrum. This would be true if this is the same gas in both cases. In one case, it's hot, so we see a bright line spectrum. In another case, it's cool, we see a dark line spectrum. Since the pattern is always the same for the same element, then an instrument can analyze the patterns and indicate what elements are present in any star. And this is the way we analyze stars and their elements. And spectral analysis shows that 76% of the matter in the universe that we've been able to find and to analyze, 76% of it is hydrogen. 23% is helium, and the remaining 1% accounts for all the other elements. Now, 76% of the matter in the universe is atomic number 1. 23% is atomic number 2. So it's thought that the elements probably arose from a primordial cloud of hydrogen gas, probably about 20 billion years ago. Now, this figure changes with different references, but an average is about 20 billion years ago. The reason we think it's a primordial cloud of hydrogen gas is because we find so much hydrogen gas out in the universe. We'll pick up our discussion next time with the chemical evolution, starting probably with the evolution of all of the elements from the original primordial gas cloud of hydrogen, and then to the development of molecular evolution. And evidence points to the idea that this evolution occurred in 3 stages. First, inorganic molecules, second, organic molecules, and finally, biochemical molecules, and then on to the origin of life itself. We'll discuss life as we know it, and we must qualify it in this way because we can only make assumptions on what we know. So we have to first of all discuss life as we know it and then hypothesize whether or not it could happen elsewhere in the cosmos. Then we'll explore the rapidly growing body of evidence to support the modern theory of the origin of life and see the cultural implications of this, to see how it affects our culture and how the culture affects it. Goodbye for now.
Pre-recorded in the studios of the Maryland Center for Public Broadcasting.